regardless of the attitude, altitude, or airspeed. Pilots find it difficult to estimate the angle of attack in flight, so instead the airspeed is used to predict when a stall will occur for a particular configuration or condition. This is called the stall speed. We'll use the lift formula to explain this concept and identify what factors may increase or decrease the stall speed. The angle of attack is a component of the coefficient of lift. As the angle of attack increases, lift increases. At 16 degrees, the aeroplane enters the stalled state. Thus, at this point, the true airspeed becomes the stall speed. For a constant 16-degree angle of attack, the formula suggests that any factor that demands more lift will increase the stall speed. Increased stall speed means that the aeroplane is more likely to stall since the safe airspeed range reduces. Let's have a look at some of the factors that may require more lift, thus increased stall speed. More weight. In straight and level flight, lift equals weight. An increase in weight needs an increase in lift, thus an increase in stalling speed. Load factor. In aeronautics, the load factor is defined as the ratio of lift to weight. You may have perceived a positive load factor as the extra weight you feel at the bottom of a slope in a fast-moving roller coaster. Similarly, an aeroplane will experience an increase in its apparent weight whilst in turn or pulling out of a dive. For example, in straight and level flight, the load factor is equal to 1, but in a 45-degree balance turn, with the help of a fancy mathematical formula, the load factor is 1.4. In such a turn, the aircraft's apparent weight increases. Its need for lift increases, thus the stall speed increases. Ice. Ice on the wings disturbs the smooth airflow over the wings, causing it to detach earlier. More lift is required to offset this problem, thus the stall speed increases. More power. More power has an opposite effect on stall speed by reducing it. For an aircraft flying at 16 degrees angle of attack, the component of the thrust vector points upwards. Increasing power increases thrust, which contributes to the lift. Furthermore, the stronger slipstream, which affects the inboard section of the wings, speeds up the airflow and helps to generate more lift. In addition, the stronger slipstream deflects the relative airflow and reduces the angle of attack. So all these factors help reduce the need for lift, thus the stall speed reduces. Extended flaps. Extended flaps increase the camber of the wings, lower the nose and generate more lift. This is what happens to the coefficient of lift versus angle of attack curve when flaps are extended. Greater ability to generate lift means that the stalling speed will reduce, but the aircraft will stall at a smaller angle of attack.